yeah, so I've been doing this open channel stuff for the last couple of years, and kind of one thing that had in common was that it was in no standard, so it's pretty much useless. So let's put it in a standard. But we also, the open channel name has kind of been used a lot, so let's kick that out of the curb and use a new name, so namespaces, so we can give it a new meaning, a new understanding, and all that. So that's kind of where we're going, and going inside here in NVMe. So there's this pretty looking slide. If I say anything about products, it means that I didn't really mean it. It's a nice things. So it's going to be all virtual devices and stuff. Okay, so open channel. Some of you might have seen these slides once or twice. So what do you get by open channel? Why is it interesting? So it's interesting because it provides three benefits. It's the I/O isolation, it's the predictable latency, and it is the data placement and I/O scheduling. So that those three kind of things that works together, and kind of why it also kind of grew on into the market was that SSDs are getting bigger. The NAND is getting bigger. Like you have 1 terabyte dies and so on. So you're like piling on more and more capacity. But the thing is, the customers that are kind of putting that data on these SSDs, it don't grow nearly as fast. So we have multiple users coming into the same SSD. And that's great, but they have different workloads. So some of them are databases, some of them are sensors like IoT, it's analytics, virtualization, video, and so on. And all that together kind of saying, if you bring that into one SSD, you're gonna put the garbage collection and so on, those algorithms within the SSD on really hard task. Cool. So we needed some way to split that out and kind of do I/O isolation and kind of do data placement on the SSD. So there was two main open channel concepts that was kind of introduced. One is chunks, where you have a chunk in the LB address space and you write sequentially. And then you're if you want to go back and write again, you have to reset it and you go back. And that's kind of how that worked out. I stole that from SAC and CPC back in the days and took the things that I thought was the good idea. Someone would probably have said it was a good idea. I took all of SAC and CPC and then we wouldn't have open channel. We just skip it right to CNS. We could have done that as well. And that's what we're doing today. And basically, it's a bit of difference between hard drives and SSDs. So hard drives, it's a single tracks and so on. You get singled and so on. On SSDs, it's about aligning that zone size to your physical characteristics of the media. So that goes together. That kind of why that's interesting, because that kind of gives you a bunch of benefits. Then the other leg of open channel was these parallel units. And there was a need where you can kind of have customers and you want to do some really strict quality of service, and you can kind of partition the drive into physical separation. And we've been really lucky that this has been solved by NVM sets and endurance groups and our TB4052 that's going now. So that's if you look at it from the open channel perspective, that's kind of half of it. And that's already done in NVMe, and we are adding a little bit of extra crust on top. So that's really great. So what we kind of seen the last couple of years is that there's obviously been the 1.2 to 2.0 open specs. And then there's been all these iterations. You have Denali, we have like the Alibaba spec, there's others that are in the wild. So they kind of flown off and kind of tied it into their architecture and what they really needed. But one of the things that kind of persisted was that we had this sequentially write-only area, chunks or zones or whatever we would like to call it, and that's a keeper. So the goal is then, hey, let's bring that into NVMe. We've been trying it out for a couple of years, seeing how it works and so on, what's the benefit, and now we know it's a solid interface. Let's put it in. So it's not brand new. We got a lot of experience with it, and that's really great. Cool. So namespaces. So it's a technical proposal that's ongoing. It's under standardization, and it gets us three things. One is it reduces the device-side write amplification. Another one is that it reduces overvisioning. So Mark Callahan from Facebook has this great quote that note that excessive overvisioning is similar to early replacement. In both cases, you buy more devices. And so we give them this and reduce the overvisioning, and we put it together, and they need less drives, But in reality, they just fill up with more drives, so we're all good. And so this is that's one of the benefits of this new interface that we're introducing. And then you have to reduce the DRAM and SSDs. There are many different ways to do it. CNS is one way to do it by introducing zones. But generally, you have this one-to-one mapping between the logical address and the physical address. And in that case, you're kind of having like an entry inside of the SSD for each of those. So you usually have 1 gigabyte of DRAM per 1 terabyte of media. And CNS is one way to reduce this kind of approach. You can also reduce the mapping table granularity. There's different things that we kind of have in the industry to kind of enable that. Cool. And one other part is that if you go off and build, in general, these kind of new architecture, you need to have software kind of enablement. You need all the software that kind of has to work together. And one of the great things we're getting here with CNS, since it follows SAC and CPC and all the hard work that they did in T10 and T13, and kind of all the work that gone into the Linux kernel, means that we could actually take CNS and mostly just bring it into the Linux kernel and be a first-class citizen. So when we have drives on the market, the software will be ready and we can start using it. So it won't be that it drives on the market and then it'll go 4 or 5 years before the software will be there. It will be like, get on the market and then you already have file system support and so on. Cool. So zones, you have the drive, you have a namespace, and then you have the zones put up linear after each other. And then what you then see is that, and then each of these zones, you write sequentially. It's the same story as OpenChannel, same thing, because it's derived from SAC and CPC, same thing. And then the idea is that, well, there was the things that we needed for hard drives, but for this signal proposal, we also need to look at how do we optimize for SSDs. So there's a little bit of things that we are sprinkled on top on the SAC and CPC approach that Tim Hatfield is kind of keeping track of and making sure that we kind of document when we are going out of bound compared to SAC and CPC. And all that together kind of, brings it in. And then, the idea is that we have a zone, same story as OpenChannel, that chunk, you align it to the media characteristics. So today, same time we had this before noon, is that we have the zone states, we kind of have the state machine brought over from SAC and CPC. We have the zone reset, that's the zone management command with the zone action that we have in the spec side. Then there's zone size, and then there's a new thing, which is the zone capacity. So NAND media in general, NAND blocks, those blocks are not a power of 2. That either may be because of the physical, how the media is made. It also can be because of the ECC scheme that you apply within the SSD. So that's usually not a power of 2, which has been very beneficial doing the, with SMR hard drives, is that, hey, you have 256 megabytes, and if you wanted to find the zone ID, you can kind of shift, and you got the LBA, shift LBA, and then you got the zone ID. Obviously, the spec, the SAC and CPC doesn't say that it should be power of 2, but that's kind of been the industry standard on how to do it. So that's one benefit. Another benefit is that, and what's kind of brought in is that the capacity, there has the zone size, and then you have the capacity. And the capacity over the lifetime of the SSD could shrink. It doesn't have to. There are bits that says if you implement it or not, but it could shrink, or it could be less than the kind of what the zone size is. So now you got a way that you can take a zone size of 256 megabytes, and the capacity can be 192 megabytes, and that's your writable area. That kind of got in there. Then the next, so that's SAC and CPC, and kind of the behavior that you kind of know and so on. That's all good. The next part is the zone append. So this is a new concept, and that's interesting both for us as it's a new concept inside of standards, like in SAC and CPC, it's not there, but it's also a really interesting concept from the software perspective, because it solves some of the coherency problems that we kind of have when you have to write down to these zones. So what kind of happens is that when you're writing to a zone, you have to guarantee that you write sequentially. In most cases, that means that you're writing your 4K or 8K or whatever you need to write, and you send it down to the drive, then you have to wait until you get a completion, and then you send down your next write, and so on, you kind of continue. And that kind of makes it that your zone is like a queue depth of 1. And you can kind of see over here to the right is that you can see that we have like for QEMU and like a bare metal server, and you kind of have like sending off IOs to a specific zone. If you're sending off to a single zone with a single writer, performance is great. But as you kind of increases up the number of writers to a particular zone, that's where kind of there's a little bit off. This one should be marking the blue one there. It kind of shows that you cannot scale. So the more writers you have to a zone, the more bottleneck you are on the host side. And that's a big overhead when it's not a big overhead for HDDs, but it's a huge overhead for SSDs where you can write hundreds of thousands of IOs per second. So for that, this kind of interface makes a lot of sense. And the idea is that, I'm going to introduce that next one, but the idea is also that we kind of, you have a zone. So when you're building up a file system, distributed file system, usually you have what is called a block allocator that kind of says, I want to write some new data, where do I go write it? And you ask this block allocator. Usually you do like a decision on a per block basis, per LBA. But for this, with zone append, you kind of take that one step further, where you say, on a big granularity, my zone size, that's where I want to write to. And then when you actually want to write, you just send the data together with which zone you wanted to write to. And it goes down to the drive. And then the drive tells you where it wrote that data within the zone. So what happened here is that instead of us having a lock for every zone, every time we have to write to a file system and figure out, hey, where do we want to go write? Now we have a data structure that kind of allows us to do this every time we write 256 megabytes instead of per IO. And that's actually both improved the performance on the host, but it also improved the performance of the drive itself because we can have multiple outstanding writers to a zone. So that's pretty cool, pretty awesome. So this is just an example to drill it in. So this is a normal zone write. When we write, we have the write pointer, we do a 4K write. We increase the write pointer, we do a 8K write. We increase the write pointer by 2 slots, like this is assuming 4K write sector size, LBA size drive. And then 16K writes. This worked great for HDDs, for SSDs, not so much. So for zone append, yeah, so that's 2 examples. The same example as before. There's a 4K write, the write pointer increases. Now we are writing to the same place. I know we are still discussing this within the TP, but yeah, we'll get it with the text and then we can work it out. And then you have like you do the 16K write and so on, and you do it. The same part but the order doesn't matter. So you can do an 8K write, and then so if the 8K came in first, hey, you'll increase by the 2 slots. And you do a 4K, you increase by 1, and you do the 16K, and you do the 4 slots addition. So this is really cool, and this is kind of for SSDs, and works both hard drives and SSDs. This is both, so you can have a local file system. This is really cool, and you can put it in and have that allocated. But you can also think of it if you want to share a hard drive across a fleet of machines, and you kind of want to say, hey, let me share that drive. Normally, you would have like one guy over here that you went to ask, hey, where can I write to? And then it tells you back, hey, I want to write to there. Oh, yeah, fair enough. In this case, you only need to do that on a per zone, so every 256 megabytes. Other thing you can do is that you can have 2 hosts share the same zone, because they can both do zone append, and they'll just get data back. So you have this little unit, and I'm trying to find Stephen Bates. It's a little bit like computational storage here. We're kind of moving a little bit of computation down, so I feel like cool and everything. Not this thin layer where you move stuff away from the SSD, you put stuff back into it. And I'm all excited about that one. Cool, so that's done a lot of work into SMR on the hard drive side. So Christoph and Martin has been very active on kind of enabling all that and putting it into the kernel. And it's very easy. So we have it running in the lab on the whole code. So the idea is that when this specification is ratified, we're going to do the same as Saki did, and together with Christoph, just drop all the patches onto, at least for the Linux kernel mailing system, mailing list, and kind of get it all in and so on. And one of the things that we want to do is that, if you had a Fusion IO drive back in the days, you had the trade-off that you had to use a lot of host DRAM. And what we kind of want to do is that we both want to remove the DRAM, extra DRAM from mapping tables within the drive, but we also want to not, if we had a host side FTL, we also don't want to have the DRAM there. So that's kind of a key problem when you kind of go into host side FTLs, is that you had this mapping table one-to-one. And what we actually want to do with this and what this enables is that we can kind of put it inside a file system. So many file systems today are log structured, so you can actually have the file system take the, when you talk about FTL, when I talk about it, I'm referring to the mapping table that the FTL maintains. The media, trimmings, threshold tuning, all that you do inside of the SSD to maintain the media, that is on the drive. That is not touching the host in any way. And that's on purpose, because we want to be able to innovate on both sides of the interface. But the idea is like we could take F2FS, which is optimized for flash, write sequentially, and we can stuff those segments that F2FS has and move it into zones. So the F2FS inside of the already existing software that we have actually acts as that mapping layer. And that's interesting because it does not have this requirement of one-to-one mapping, so it doesn't have 1 gigabyte of DRAM per 1 terabyte of media, but it also becomes part of the file system. It's work that we already had to do. So now, before we had to do both on the drive side and on the host side, we had to do this work. And it, of course, cost some power to do that and all the extra logic and so on. Now we have those things collapsed into the same, and we are actually getting a win of it. So we're getting a more efficient architecture. Because this work that the file system is doing, we already had to do that on the host side. Cool. Another part is that an SMR hard drive has kind of been used the last couple of years and is really ramping up volume over the next, already this year, but also the next couple of years. It says like half of the hard drives that's going to be shipped is going to be SMR hard drives. So we're actually ramping up very quickly on this new type of storage. Cool. So just to give you a little bit of a where we are. So that's kind of what we've been doing, kind of at least on the software side. We've been doing it in WD is kind of enable this host stack. And the thing is that you kind of have a block device and you need to tell it I'm a zone block device. That's all. So when you plug in a CNS drive, this is a virtual CNS drive. When you plug it in, it shows up at a host managed drive. The next part is that we have is this, where you have chunk sectors. So in Linux speak, that's the zone size, and it's given in 512 byte sectors. And this shows as a 1 gigabyte size. So all this works today. The next part is that we had these zones that we talked about that we kind of want to get the information out. And there we also have it like, so we enable an NVMe CLI and so on. We have a zone log. We can kind of get out like the start LBA, the write pointer, the capacity, what's the state is empty, and so on. It's sequential write only, and so on. So all those things kind of have in and have working. So yeah. And then the last part is I talked about file systems and why that was kind of interesting. So we actually trying, we have done it for F2FS. We are trying to also enable it for BODFS and XFS. We'll see if we do it in time for the spec is ratified, but it's on the roadmap to get that done. So F2FS is a file system that usually used on mobile phones. So it's less used it, but it's very used in that area. The cool thing about it is that it already has zone support. So that means we can tag into that already and use that as kind of a base. So that's what we did. So we didn't do any changes to CNS. We did a little bit on the NVMe device driver and the block layer, and then a little bit of teaching F2FS about zone capacity. But in general, that was all it took. So we kind of have this kind of infrastructure. So we could actually just go in and say, create a file system, point F2FS, make FS, point it to the zone block device, and it will be created. It will create the metadata because it understands the zones and all that. And the kind of formats is successful. So the cool part, since F2FS is a log structure-based system, it kind of has this concept of overvisioning. So here you can say, give me a 3% overvisioning, 20% overvisioning, and so on. All that is baked into F2FS. Yeah, and we can mount the file system. We can list the files. There's no files at this point. Then we can create a file, reduce DRAM, overvisioning, and firmware complexity. Yay! And then list it again, boom, and then we see the same thing in the file comes out. And then the thing is, I just showed here that we read and write, that's great. Usually some of you will say, hey, resolve it in the page cache. That is true. But we could also just do an unmount, reboot the system and come back up, and the data will still be there. That is very much it. It has been a great ride so far inside of the TP. We formed a sub-team. A lot of you are members of that sub-team, and it's kind of helping making this possible. I know a lot about how I wanted to look on SSDs, but honestly, I didn't know enough of it on the SAC and CPC side and all the things that we kind of pulling together on what else we need in NVMe. So this is very much a team effort of everyone involved, and I'm very happy to be part of it. Thanks, that's all I have.